Welcome back to our lesson 27, and thanks for always watching our lessons. Pure mathematics, we have indeed moved. Now, today we need to learn what sequences and what series are. We need to get the difference between the two, and it is at that level that we shall discuss in detail the various and most important series at our advanced level of learning. Now, when you look at these two words, they move together. One comes from the other. And I'll start by defining what a sequence is. A sequence is a set of numbers, stated in a definite order, set of numbers stated in a definite order, whereby obtaining the next number from the previous one, there is a certain rule you follow. I've said a sequence is a set of numbers stated in a definite order, such that each number is obtained from the previous one, such that each number is obtained from the previous one following a certain condition, or rule. What am I trying to say? A set of numbers stated in a definite order, such that each number is obtained from the previous one, but following a certain rule. Each number in a sequence, each number in a sequence is called a term. And even underline that one. Each number is called what? A term. Consider the following sequences. Roman 1 can have 2, 3, 5, 7, 11, 13, and so on. Roman 2, we can have 1, 4, 9, 16, 25, 36, and so on. There is a comma there. Roman 3 can also have 1, 3, 6, 10, 15, 21, and so on, and so on. Now, I'm going back here. A set of numbers stated in a definite order such that each number is obtained from the previous one following a certain condition. Let's look at these three. I can even add on one more. We can have 1, 8, 27, 64, 125, and so on. When you look at this sequence here, the first number is 2, the second one is 3, the third one is 5. Critically, you can see that this set is containing prime numbers. So it is a sequence of prime numbers. We are following a certain rule to obtain one after another. If you look at the second one, we have 1, we have 4, we have 9, we have 16. When you look at these ones critically, it is a set of square numbers starting from 1 and beyond. The rule is to obtain the next number from the other, you have to square positive integers as they flow. When you look at the third one, we have triangular numbers. You see, from 1 to 3, can add the 2 here. From 3 to 6, you can add the 3 here. From 6 to 10, you can add the 4. From 10 to 15, you can add the 5. From 15 to 21, you can add the 6. A certain rule is being followed to generate. As a reminder, I've said, each number in the sequence is called a term. So, in the first sequence here, 2 is the first term, 3 is the second term, 5 is the third term, and so on. When you look at this sequence here, 1 is the first term, and what? And so on. And so on. So, I'm trying to emphasize what a sequence is, and I've tried to give some examples. By the way, each and everything has got a significance. That's why I've also told you that each number, so we are going to cease calling them numbers and we start calling them terms. If you are dealing with sequences and series, you are not going to call this the first number. You will call it the first term, because we are saying each number is called a term. So it depends on where the number is placed. That's why I've called this the first what? The first term, because it is placed in the first position. Because it is placed in the first position. Now, the dashes in brackets at the end of each sequence, the end of each sequence, show that each one could go on indefinitely. show that each sequence can go on indefinitely. i.e., it has no end. It has no end. When you come back here, ever after a given term, there is a comma, but I've reached somewhere and pressed there those dashes. Those dashes indicate that on each sequence we have other terms we have not mentioned, so this sequence can go on indefinitely, and such a sequence is called an indefinite sequence. In other words, these sequences I've listed here have no end. They can go on and on. They can go on and on. Why? The presence of these dashes, they indicate that we don't have a stopping position. They are moving on up to the end. Now, but should we restrict our solves to a certain number of terms of a sequence, to a certain number of terms of a sequence, comma, to a certain number of terms of a sequence, e.g. can have 2, 3, 5, 7, 11, 13, and I stop at 29. If I wish to restrict myself up to a certain number of terms, and I've given an example of a sequence like this one, the final single full stop indicates that the sequence has an end, and such is called a finite sequence. Is called a finite sequence. Are you getting the difference between these two? The finite and indefinite sequence. I've said each of these numbers is called a term. I've also talked of these dashes here, and I've said that those dashes indicate that the sequence can move on and on up to infinity. That's why I've said it is called an infinite sequence. Then if we restrict ourselves to a certain number, we end up with a certain value where that sequence, or a certain term where that sequence is ending. And I've said, with that case, such a sequence is called a finite sequence. Such a sequence is called a finite sequence. Note, it is very important to note that an expression for the nth term, sometimes called the last term, is very vital in sequences and series. Sequences and series. i.e., that nth term is denoted by UN. It is capital U, then subscript N. Now, in each and every sequence stroke series, we have what we call the nth term. That term is the one that will determine which number will follow the other and in a definite order. Which number will follow the other in a definite order. For instance, ig 1, 4, 9, 16, 25, 36, and so on, has its nth term as n squared. What does that mean? For un is equal to n squared, u1 will be 1 squared, u2 will be 2 squared, which is 4, this is 1, u3 will be 3 squared, which is 9, e.t.c. So the nth term of any sequence stroke series is very important because it can guide us in determining which term is coming after another. Which term is coming after another. You look at this one. We have 1, 3, 5, 7, 9, 11, etc. and so on. When you look at this one, its nth term is 2n minus 1, i.e. un is equal to 2n minus 1. The nth term, this one, can be helpful to determine each and every term in this sequence here. For instance, u1, that is the first term, is going to be 2 times 1 minus 1, which will give you 1. U2 will be 2 times 2 minus 1, which will give you 3, and so on. And so on. So we are going to pick it up from there in our next lesson.